Hi there. Welcome to lecture 22 of Machine Learning from Data. And we are going to look at how all the good stuff that we learned in the foundations part of this course is going to apply to neural networks. Okay? And remember, I told you, you can never escape the foundations. They're going to be with us, no matter what we do. Okay, so basically we will address approximation versus generalization and how that surfaces in neural networks. And then we'll have to address overfitting. Okay, so regularization and a specific technique for, regularization called early stopping, which can be applied to any iterative algorithm. And lastly, we'll sort of address a little bit the second step of learning, which is how you get in-sample error small. So we'll talk a little bit about minimizing the in-sample error more efficiently. Basically, how do we beef up gradient descent? Because it turns out that fitting the data with neural networks is indeed a challenge because there are lots of local minima, and also, the computation is itself costly, it's challenging. So we need efficient algorithms to minimize the in-sample error. Okay, and there's a whole field of optimization that deals with such, what is called non-convex optimization. Obviously, we're not going to cover that whole field, but let's, dip our feet in a little bit here and there. Okay, now what did we do last time? Last time we addressed how do we fit, neural networks to data at a very basic level in some sense. Okay, so when you specify a neural network, you tell me what are the weights. Okay, and now given the weights, I can compute the output, h of x for any input x. Okay, and that's the forward propagation algorithm. Okay, and you start with x, and then you propagate forward to the output. Well, that becomes the output of layer 0, and then you propagate forward to the output of layer 1, and then the output of layer 2, and so on until you get to the output of layer L. Okay, and then that's the, that's h of x. Okay, now, of course, that you can compute the output once you have chosen the weights, all the weight matrices that are going into every layer. Okay, but when it comes to choosing those weight matrices, we need a principled way to choose them, and the natural way is to fit, the neural network to the data, i.e., choose the weights, choose all your weight matrices to minimize the in-sample. And that's non-trivial because minimizing the in-sample error involves computing a gradient. Okay, and how do we compute a gradient? How do we compute a derivative of a function that we haven't even mathematically specified? Because forward propagation, which allows us to compute h of x, is not a mathematical specification of h of x, it's an algorithmic, specification of h of x. I give you an algorithm to compute h of x, which is forward propagation. Okay, so we need to develop a sort of parallel algorithm that computes the gradient. Okay, and that's what backpropagation essentially did. So what we did last time was, we said, okay, so for a given set of weights and an input x, you have an error, and we can compute all the outputs at every layer, including the last layer, which gives us h of x. And what we're interested in now is how would the error E change if I change the weights a little bit. Let's say the weight matrix WL into one layer. And we derive this fundamental equation here. Okay, which is that the derivative of the error with respect to the weights is the output of the previous layer, okay, multiplied by a sensitivity that's specific to the layer into which the weights are going. Okay, this delta L. And the meat of the backpropagation algorithm is to give a dynamic program, a backwards flowing algorithm that starts by computing delta for the output layer and then goes backwards one by one and computes all the deltas. Okay, so that's the backpropagation algorithm. Now, it doesn't make sense for me to go into the details of any of these things because it's hard to realize, it's hard to follow, it's hard to sort of grasp in real time. Okay, so you need to read carefully now the derivation that we did last time, the text, and ultimately you're only going to learn it when you implement it. Then you will see the nuts and bolts of backpropagation working and gradient descent with neural networks working. Okay, but we took a small neural network. Okay, with our two input features, intensity and symmetry for digits, we took 10 nodes in the first hidden layer, and there was only one hidden layer. So this is a baby neural network, and look at the level of overfitting that we can accomplish. Fantastic. Okay, we need to address this at some point today. Okay. And I also showcased, gradient descent versus stochastic gradient descent. And here the goal is just to minimize the in-sample error. So step 2. So the picture on the bottom is step 1. We clearly have fit the data well, but forget about E out here. This is just a total overfit. Okay. And step 2, how do we get the in-sample error low? Well, there are many algorithms. Okay, so we're now, suggesting stochastic gradient descent in this picture, but we will see that there are even more powerful algorithms. Okay. And so the goal for today is to sort of look at approximation versus generalization, address overfitting, And then talk a little bit about, how we minimize the in-sample error more efficiently. Okay? Because, training big networks on lots of data is a computational challenge, A. And B, there are lots of local minima. Okay, so, how do we address some of these issues? Okay, and let's go to the board. Okay, so let's start by looking at approximation versus generalization. Now, when we discussed universal approximation, remember I told you, you don't need deep networks, okay? In fact, a single hidden layer suffices, providing you give me as many nodes as I want in that single hidden layer. And what does each node in the hidden layer implement? It implements a perceptron, okay? So let's focus the discussion, on the single hidden layer neural network, even though in practice you may want to use deep networks with multiple hidden layers, okay? So let me show you what a single hidden layer neural network looks like. Just this is a reminder. Okay, so you have your input X, okay, and you have your hidden layer nodes. Okay, so I'll put them in sort of red here. Okay, and so you have your augmented one. Okay, and let us suppose that you have M. So you have M nodes in the hidden layer, okay, and your input has D dimensions, so this guy has D dimensions, okay, and so there are actually D plus 1 vertices here with the augmented one, so there's an augmented one here, okay, and now I'll remind you, what does each of these hidden units, we call them hidden units, what do they do? They implement a perceptron. Okay. Each of these implements a perceptron. Okay. And we call this the weight matrix W1. Okay. And then we have a final layer perceptron. Okay, nice. So we have a final layer perceptron. Okay, which produces H of X. Okay, so this is the one hidden layer neural network, and the basic parameter that you get to control is M, the number of hidden units. Okay, now, we had that very precise systematic notation for the general neural network, which we need because you have many layers. Okay, but it's a little bit cumbersome to use all that notation for this simple, one hidden layer neural network. So let me simplify the notation, and we will call this perceptron, well, you define the perceptron by its weights, so we will, since this is hidden unit 1, we will call these weights V1, and these weights V2, and these weights V, and these weights V3, and so on, up to Vn. Okay, so what's coming out of here? Okay, what's coming out of here is essentially the sign. Okay, the theta is coming out. What's coming out of here is theta of Vi transpose. Okay, X. That's what's coming out of here. Okay, and then we'll call these weights W. So you have W0. So you have W0, W1, W2, and so on up to Wm. Okay, because you have m hidden units. Okay, and so what is H of X? Well, H of X takes each of the perceptron outputs, which is of the form, so you'll have V1 transpose X, V2 transpose X. So you'll have, theta of V1 transpose X, theta of V2 transpose X, theta of V3 transpose X, and so on, theta of Vm transpose X. Okay, nice. Okay, and what we're going to do is we're going to multiply each of these by W1, W2, W3. That's what this perceptron does, Wm. Okay, add the W0 and add all these up and apply a function theta again. Okay, so the output H of X is equal to theta of W0 plus the sum from J equals 1 to M of theta of Vj transpose X. Okay, and so let us call this the neural network. We'll call it the neural network, although technically it's the single hidden layer neural network with m hidden units. So I'll just call this the neural network. Okay, nice. Now, just to show you the progression that we have gone through, let me compare this single hidden layer neural network with some of the other models that we have seen. Okay, so let's start with the linear model with the nonlinear transform phi. So linear model, linear model with phi of x, okay, which is equal to, which has an augmented 1, and then phi 1 of x, phi 2 of x, all the way to phi, remember we called it d tilde of x. But now let me imagine, just for comparison purposes, that d tilde is m. So we go into an m-dimensional space, phi m of x. Okay, so what was the linear model? Well, depending on what the type of problem was, regression versus logistic regression versus classification, we would change this theta into either sign, identity, or sigmoid. Okay, so I'll just write it as theta of W0 plus the sum from j equals 1 to m phi j of x. Okay, so that's the linear model with nonlinear transform phi. And now let me show you one more model that we have seen, which is the radial basis function network. The radial basis function network, RBF network. Okay, with kernel phi, and typically we use the Gaussian kernel. So with kernel phi. Okay, so let me write down what's that hypothesis that's computed h of x. Okay, so this is theta of W0 plus the sum. Okay, so now let's assume that we are doing the RBF network with m centers, so m bumps. So then we have the sum from j equals 1 to m. Okay, so this is here k equals m. Here z space dimension equals m. This is just to compare. Okay, so k equals m. We have phi of what? Okay, so here we're talking about h of x equals, and h of x equals, okay, phi of what? Okay, phi of x minus mu j over r, okay, and we had a magnitude here, okay, and we take the linear model, so wj, so we take the linear model, okay, with similarity features. So it's very similar to the linear model with the nonlinear feature transform. What was the difference with the RBF network? The features were specific features. They were similarity features, specifically the similarity between x and the center mu j. Okay. Now, when I write all these models, you should see a striking similarity. They're all basically a linear model. Okay. Sorry, I left out the WJ here. The WJ. They're all basically linear models. What do I mean by basically linear models? So here, we're implementing a linear model in the final layer. W's. Here we're implementing a linear model in the Z space. And again, I forgot the WJ. Okay. We're implementing a linear model in the Z space. W's. Okay. Here, we're implementing a linear model in a Z space in some sense. Okay, but this is a Z space, a very specific Z space where the features are similarity features. Similarities of the input x to some centers mu j. Okay? And so here, the function depends on what's your measure of similarity. Here, the function depends on what's your feature transform. Okay? And here, the function depends on what are your perceptrons being implemented here. Okay, the specific linear model. Okay, so these are very similar. And that's what I told you. The linear model is going to be there everywhere. Okay, but now let's pinpoint the fundamental differences. Okay, let's pinpoint the fundamental differences. Okay, so when we talked about, the linear model with the nonlinear feature transform, we were very emphatic. We said that you have to choose your feature transform phi before you see the data. Okay, so let's call this, the simplest situation. And we know that when you've picked your feature transform before you look at the data, we can apply the rigorous, E in to E out bound. Okay, so feature transform phi picked before looking at data. Okay, that's the nonlinear feature transform. Tell me what it is before you see the data. Let's look at the RBF network. Okay. Slightly more complicated. Okay, slightly more sophistication needed. Okay, because we don't know what the feature transform is. We don't know how to compute similarity features until you tell me the mu j's. And in principle, I can pick the mu j's to fit the data. Okay, so with respect to the w's, yes, it's a linear model, but it's nonlinear with respect to the mu j's. Now, what did we say when we talked about the RBF network? We said, you know what? Based on the philosophy behind how it was derived and the philosophy behind, we're placing bumps on the data in order to represent the data, we said that we can pick the mu j's, okay, in an unsupervised way to just be the centers of clusters that represent the data. Okay. So here we picked, let's call it the similarity features, i.e. mu j, in an unsupervised way to, represent the data. Okay. Represent meaning we're going to place bumps around the data, and we'll choose the bump centers in order to represent, where are the data points. Okay. And here, okay, what's the feature transform? What's the nonlinear feature transform? It's the nonlinear feature transform is given by these perceptrons that are implemented. Wow. Okay. The nonlinear feature transform is given by the perceptrons that are implemented. So here, we are mildly looking at the data, okay, in order to decide what's our feature transform. Here, the features, you can think of this guy here as, an analogous to phi j of x. Instead, it's theta of vj of x, vj times x. So this here is phi j. Okay, and we are going to optimize these weights by fitting them to the data using gradient descent and backpropagation. Okay, so we are going to fit our features to the data in a very real way using both x and y. So here, fixed features, fixed feature transform. Here, mildly fit feature transform. Fit mildly because you only need to look at the x values in the data to pick bump centers. So mildly fit, okay. Fully fit features. Okay. So here, Vj are optimized to fit the data, okay, just like the W's. Okay. That means, okay, that our features that we are using in this linear model have been, intricately fit to the data. Features fit to the data. We are picking features based on looking at the data. Here, phi is picked before looking at the phi, i.e. the features, i.e. features. Okay. Now, at a very high level, that is the sophistication that the neural network brings. Okay. It allows us to fine-tune features to the data. No fine-tuning of features to the data. You pick your nonlinear transform ahead of time. Mild fine-tuning of features to the data. So you can see, least amount of fine-tuning of features, a little bit more, the more. Humongous power. And that's what we saw in that picture when I showed you the overfitting to the digits. You are allowing me to fit my features to the data. And then, okay, I'm going to use a linear model on top of that. But that power to fit the features to the data is a humongous power. Okay, and I'll put it in blue now. Humongous power. Okay, and let's investigate that humongous power. Okay, because we need to control it. Okay, so specifically. Okay, and now you can see, it's beyond the scope of this course to get into the analysis which derives these kind of results. But specifically, this neural network, okay, achieves E in is O of 1 over m for regression, O of 1 over square root of m for classification. Okay, so basically, what is this saying? Okay, that if you give me, so this is, on no matter how many data points you have. Okay, no matter how many data points you have. Now, this is assuming in some sense that there's no noise. If there's noise, you can't really escape from the noise. Okay, so as long as there's no noise. Okay. If there's noise, you've got the best you can do, which is related to the noise, then plus order of 1 over n. Okay, so this is regression, this is classification. What is it saying? What it's saying is that if you allow me to increase my number of hidden units, I will fit the data. I will do what? I will fit the data. Okay. And the rate at which my in-sample error is going to 0 can be quantified in terms of the power you give me. And this is a very powerful result. Okay, basically it says, put more hidden units, you'll fit the data. Okay, and that's related to, the fact that we get to fine-tune the features to the data. Now here, you give me more and more dimensional feature transform, okay, but as you give me more and more data, if you give me much more data than the number of dimensions I have, I may not be able to fit the data because I have to pick my feature transform before I look at the data. Okay, I have to pick my feature transform before I look at the data. And here, I'm only allowed to look at the x values in order to pick my feature transform, and that might not be sufficient. Even if you give me lots of x values, it may not be, I may not be able to fit the data with similarity features unless you give me m approximately equal to n or root n. Okay, if you give me lots of centers, then I can fit the data. Okay, and a similar result is going on here. If you give me m large enough, I can fit the data. Good. Okay. And no matter what the data size is, the data size is getting larger and larger and larger. Okay, so we have to now see how do we get the link from E into E out. So we have to, so this is the approximation capability. So this is the approximation capability of neural network. And this is just single hidden layer. Okay. So let's erase, and talk about, how do we rein this power in? How do we stop overfitting the data? We need to talk about, generalization. So this is approximation. Let's talk about generalization.